Welcome to part 4 of looking at this Heathkit H8, H9 and H17 combination. This one's also a look at the logic analyzer and the use of them for diagnosing a problem. So it's a bit of a dual episode that covers a look at that device and the H85 serial card, diagnosing the problem with that card, and we'll also get on to an initial look at the H17 disk drive and strip out the control board before the end of the video. Hopefully you're going to enjoy. If you remember in part 3, after fixing the memory, we'd left it worked out that the address lines were obviously triggering whenever the address for the serial port was being selected was correct, and then some other chips were taking effect to select the buffers to allow the data in or out of the card. So that needed, in order to make sure that decoding was all working correctly, that we use more than just an oscilloscope where you can see 1 or 2 channels, and I used a small logic analyzer, which I have a little 8-channel USB one that goes onto the laptop and lets you gather quite a bit of data, and is usually quite useful in these sort of environments. The difficulty was didn't really give enough ability to select specific addresses and granularity, so I had to finally break out the not that long ago acquired HP analyzer. So I'm still trying to diagnose what's wrong with this I/O card and why I don't see any characters out of the USART. I've had to break out a slightly bigger data analyzer on the Benton Harbour bus. As you can see, it's all wired up to the pods, so you've got basically the 3 pods with the clock ability set up to come off the O2 clock, and the address and data lines. I'm also reading the memory. The majority of the other signals are actually picked up with clips on the chips, as we were doing with the smaller signal analyzer, because you actually have to get through the buffers as well. And you can tell that because you see in the select signals and so on. We'll have a little quick discussion about that. I did capture some footage of the setup of the analyzer, but unfortunately the screen does have quite a bit of wobble, which is incredibly pronounced when you're seeing it in the camera. And in fact got quite bad, so I do need to do a little bit of maintenance, so we'll probably see the analyzer in another video in a bit more detail. Okay, so hoping you can see the screen okay. If not, I'll try zooming in occasionally just so you can see the general layout of the buttons and things like that. But the first one I'm going to do is obviously use the format to go to the setup screen in terms of what we've got configured where. And the first one is you've got 3 clock connections on the pods. I'm just going to use the first clock now because we're on the Benton Harbour bus. The clock is inverted, so I need to use next to change that to you'll see if we zoom in a bit, hopefully, that it's just an up arrow. So I'm just going to change the next to change that to a down arrow, which is so downwards clock. If I just use next, actually it would have gone downwards. I've gone right the way through, no clock, up, down, so just the edge. Next we're going to have to change some of the settings to it. I don't need to use the multiplexing because the bus is already decoded by the card, because obviously the 8080 puts some of its signals out in different areas and some processors do other things. So I'm going to change the first label to be the address high, maybe. So A, D, B, and then R is you need the shift button, so address. And then for H, we're going to have to do a H, and again it's on the bus, so it's a negative bus, so I need to change it so it's negative. And now we've got a row of asterisks for which parts of the system we're interested in. And for address low, I'm interested in only in pod 3, so I'm going to not care about, so I'm going to use next to change it to a dot on all the pods except for pod 3, and it's going to be just the bits 7 down to 0 because there's 9 bits of capture on each of them. So we'll leave those as stars, and then I don't want anything on any of the other pods for that address high. And then I'm going to insert a new one, which is going to be address low, which is again going to be negative. And in this case it's always not interested. The first one's always interested in things, and I'm going to make it interested in the bottom 7 bits of pod 2, bottom 8 bits of pod 2. And then I'm going to insert another one, and we'll take a look at the M1 line on this thing. So M1, which is actually on the, it doesn't really matter whether we see it as a 1 or a 0, it's only 1 bit. We're not going to be turning into numbers. And that is the M1 line, I think, is actually on the top bit of pod 4. That'll be here. And then we're going to insert, now we're going to want a data line. So we'll have DA, TA, and this is going to be the rest of pod 4. So that should be enough for us to start getting a bit of an interest. What I might do then is we'll insert another one. That should be enough for us to take a little look at that one. So now in theory, if I hit, if we go into trace, I haven't got anything specific set up, so we'll just see everything that this device captures. And obviously it's just got some stuff in it, but we see in the actual things. Now what I'm going to do is I'm going to change the address high to be octal, and we're going to change the address low to be octal as well, because by doing it in 2 halves it gives us the split octal that the H8 uses. The M1 is a hex line, but you just see 1 digit anyway, so it doesn't matter. The data I'm going to see in hex, because I recognise things in hex quite quickly. And IORW we're going to change to binary, because we want to be able to see the 2 bits. And we'll do the same with the status bit. And we'll do the same with the chip enable bit in binary. There we go. Okay, so now we should be able to see a capture and see what it is. I mean, this capture from earlier, which is why it looks like it's real data before I'd set the machine up. So if I turn the machine on and we do a run, it's going to capture a set of things that have happened on the machine while we've been running, and we can see it's a selection of executed instructions. We can see the M1 line going high. So obviously there's more than just that captured as well, so we use the roll buttons in order to scroll down through the actual instructions that have been executed. As soon as the screen wobble, the video here, we need to fix the CRT a little bit, I think. That's quite pronounced actually, isn't it? It's going to make me sick. Just pick up where we left off with the film. It's been set up now to capture when he outputs the port, which it does. As I'm really getting nothing, the only thing I can think of is maybe the USAR is faulty. So hopefully you can see the HP setup. I'm sure Lisa will be fascinated to see this actually in use. The small 8 channel just wasn't enough because I need to be able to select addresses. So what I've done, I've actually set up the split octal so that you can see the octal readouts that will correspond to the front panel addressing, so upper and lowercase. And on the upper range, I've given it some clues about what is in that area. So I've used the labelling function to say whether it's in the monitor or in the RAM. And I've set up a trigger. So we've basically got the bits set out, but I've also got on the trace, I am tracing on octal address 372 in the low, and the right line 1, I don't care, that don't care button obviously for this one. For the read data, it should always be, you should never have them both at the same time, but I want a 1 in the right. So I think that's about it really. It's just if I run the trace, it's set to trigger on the first occurrence of the write to that address, so I've already got the third stage of the test set up on here. So if I hit the out button, then of course it does trigger because it sees the write to address 372, and it's writing 101 octal, which is correct, which is the ASCII A. So you can see that obviously once it comes out and then it goes into another M1 cycle, picks up the next instruction from the microprocessor. But we still see nothing stubbornly coming out of the UART. I mean, the other interesting point, I suppose, is this status bit being a 1-0. That's the CE chip enable out on that pin, which is, so that's the data in enable. So we see it, but we don't see a write back out onto the data bus from the output of pin 6 on IC118, and pin 6 IC118 is the blue wire here, which is just checking, goes into the 2 on the format, so it will be the second on pod 2, so it's that one. So it is supposed to be, long story short then, I was right, the configuration was okay. There was an order placed on eBay for a USART chip. We'll pick up and see where we go. Excuse the handheld video, but when I press the out button on this should send a character A to port 372 on the what is the replaced UART, and on that screen we should see an A appear again, as it has done there. Look at that, A. We should see just on the screen occasionally, yeah, we're capturing it. Now in theory I can do an in as well to read the data that's on the port, which is blank. If I press a letter on the keyboard, so let's press N, obviously it blanks because it creates an interrupt. Well, I should be able to reset and go back to where we were and do an in, and there we go, we got 156, which I believe is a H. So if I do an out on that, that should appear on the screen and echo back to the machine. And no, it didn't for some reason. Probably because the UART has been reset and we need to reset those things. Okay. That was a pretty good result then, working out what was actually wrong was the USART chip was completely fried. I didn't capture any footage, but I also took a quick look at the USART on the cassette side of the interface. If you swap the initial diagnosis, I swapped that USART chip into the serial side, and that just locked the H8 up because it had a permanent IRQ present, which just completely floored the machine, of course. So both USARTs turned out to be faulty. I wish I'd ordered two, but long story short, I did actually get a second USART for the cassette side, but I haven't really progressed because we're going to go a little bit back in time now to before part 3, where I fixed the RAM cards. While I was waiting for the chips to arrive, which was quite some time, I obviously decided to dive into the H17 disk system and have a little look at that, which is why you will find when I discover that the H17 controller card actually has the memory test routine built in. That would have been handy to know beforehand and know that the card worked, because I could have done a lot of the RAM testing far more quickly. So we will see the RAM test fault show up as part of the filming. Just remember it's slightly out of sequence time-wise. The magic of television. So let's see where we get with the H17 disk drives. We start with actually the drive itself, which has an obvious burn mark, as we saw early on in the initial analysis with those capacitors. New day, new table layout. As you can see, I've got the H17 disk unit on a dim bulb to make sure the caps don't just go bang. Been on there for about half an hour, looking okay. We seem to have 5 volts and 12 volts on the connectors for the disk drive. Last night I made some more progress, not on camera, on the 16K RAM. I've managed to prove that it's two chips, two bits that are faulty. I think it may be more than one chip because there's two bits at each position. I was going to have a little investigate of that today. I took a chance and once I proved that, I plugged in the controller board and started checking some of the first functions on that, because it's got a built-in memory test at 030003 which you can run to save you typing in the memory test all the time. It's made you a bit faster to diagnose the 16K RAM fault where it is. It just seems to be really lucky that the RAM fault is in an area I was in, the sort of top bank of the 4 banks, and so in the top 4K chips. But it wasn't actually present in the rows at the very top of RAM which it picks to become the stack. So by pure dint of luck, the first 3 banks of 4K run fine and test okay, and the top bank didn't. What I've done is I moved the faulty chips to the 3rd bank, and it moved exactly, each of the addresses moved with it to the 103 range. So 99% certain there's a few chips in there. I did want to do a bit more today, maybe on camera, to look at which bits it was exactly, because it may be more than 2 of the chips that are faulty. There's quite a few addresses, I think about 8 that have got faults. Some seem to have stuck 1 bit and some seem to be able to go to 1. So that probably indicates probably 4 chips are faulty in that row. Of course they're pretty hard to get hold of, not when I got in stock, etc, etc. And there's gold cap ceramic ones, so I'm not going to be able to replace them like for like. I have managed to find someone selling some at a pretty eye-watering price online, so I've ordered a bank of 8. I thought if they can have plastic on it, I'll just swap a whole bank out, and chances are there's going to be, if there's 4 gone, there might be a 5th that we don't know about or will show up. So I might as well get a bank of 8 swapped out, and that'll give me a couple of spares for the other row banks. I'll probably get the 4K RAM card running as well. I've ordered some chips for that because I think it's 6 of the 8 are faulty on that, although we can again do a little bit more testing now that we've got the memory testing ROM on the controller card working. And as I said, the memory on the controller card for the H17 tests okay as well, the onboard RAM, and obviously the ROM is working because it's running the ROM routines. The rails are fine on it as well, nice and stable regulators. As you can see, I've left the spaghetti dangling out in case we need to use the analyzer for any work. But now we're going to need to take a little bit look at where I've got with the board on the H17. You've probably seen a photograph by now of some of the damage that I saw when I first saw it, which seems to be, they are tantalum bullet capacitors I think, but I would probably be fine to swap them for electrolytics on where they are. I need to see if that's actually the circuit of this board. I think this is a very early version of the board that was supplied by Heathkit. I think it might well be a WANGCO, which is the first one they used in these when they first released the machine. This is got a disc with it, as I said, dated from 1979, so it's version 4 of H17. So chances are they could have switched to the Siemens drives maybe. I'm not experienced enough to be able to identify them visually, but this does look like a very early board. There must be a drive speed control board somewhere as well on that drive, so probably have to get it out and lubricate the drive, clean it all off. All the old lubricant will have gone seized. You just clean that off with some isopropyl and some very light machine oil, just dabbed into 1 or 2 places where there's contact. Should get the drive freed, mechanism freed up and running. And then we'll try it with a sacrificial soft sector disc that I can afford to run, and we should be able to use the diagnostics from the manual. I didn't find those online actually, so we need to maybe scan those in and provide them to the community, but I should be able to run some of the diagnostics to check on the state of what's happening with, we should be able to see at least the sector pulses coming out on the scope and things like that, just to check the drive's basic functionality before we try and put a disc in there. I'm even tempted, now I've got the serial port working with that faulty USART replaced, to try and get hold of a copy of the short loader that you can put in that allows you to load software, so I can create a new disc and maybe try and hand punch an old floppy into some of the 11 hard sector holes, might be possible. I think my paper punch looks just about the right hole size, the hand editor. So we'll give it a go. So I'm going to get that board out, which you can see has got these dead capacitors in. Definitely, there might be some resistors that are gone as well, so we'll give it a little bit of a clean and just check everything visually under the scope, on at least a hand magnifying glass. Replace the caps that are obviously blown. I might even replace all the bullet caps. Perhaps there's another one definitely down here as well. Chances are it might just go. Although if we bring it up slowly, it should survive if they're tantalum. Typical, wrong side screwdrivers. Yep, no, need to go get a rubber screwdriver. Okay. Right, correct tools for the job. Board should lift off neatly. Yes, it does indeed. So as you can see, the board is pretty grubby, and we need to give it a good little bright light and have a good look at all those caps. Finds of any other burning on the board. There's obviously been a rework on that chip there at some point in the past, and I suspect that socketed one, I don't know, sometimes they just socketed them because they couldn't have that chip when they made the board and they'd add it later. It does need a bit of a blow off, just to clean off the worst of the gunk. And let's just hope the unusual regulator ICs are all okay. Good visual inspection, and we'll come back to it and look at disassembly. The actual drive mechanism itself does look a little bit grubby, so we'll have to take a look at that. Won't be a very slow pan, sorry, but you can see the drive. Oh wait, there we go. So it's with the worm drive here we'll need, and that will definitely need a bit of this little tiny bit of corrosion on there. Probably need cleaning off. Doesn't look that bad actually. The head will probably need a bit of isopropyl. Sensor wire looks okay, maybe. That's the sector detector. This raise and lower mechanisms, alright, on the metalwork, so it's quite smooth actually. So I suppose we'll have to have a look at how the motor is driven as well underneath. So we need to get this out of the chassis, which I think means we've got to take it apart completely. And that's, I think, can you see that? I wonder whether he was a smoker, because I'm sure down there is a cigarette. If we put a bit of light on that. We can see it actually. Can we? Yep, there we go. Well. Things you find in old computers, eh? High-res photo of this as well as it stands, just so that we can take a look at it. Having extracted that board, we're now going to the rest of the video is quite a detailed look at the repairs. There isn't anything afterwards, so if you're not interested in seeing a board level repair, feel free to fast forward or skip to the next video as soon as it arrives, and we'll see you in part 5, where we'll delve into getting that drive running. Okay, I think this is not the board that we've got the online circuit diagrams for, but as a minimum we're going to take off the known dead caps, and I'll probably take C23 off as well, just because C23 looks a little bit charred next to C21. Can't quite see the values as well, that's going to be a shame, but never mind. Blown cap should come out. You might be able to see the value of the board, the value of it once it's out of the board rather. I can't see the guy next to him. It doesn't look too bad. That one there, C22. I can't see the name of him and what is. Yeah, he's got some charring on the outside. It's not going to do him any favours, is it? I actually found ejections from this particular cap. I found some ejected material all over the spread, all over the board. We can't quite see what its value is. Yeah, it's very difficult to see. Definitely not visible. 20 volt. And this one, the charring has taken the ability to read the value on this one as well, which is C22. That board has definitely got a bit of charring on it. So hopefully now we should be able to see the charring on the cap, where the board is. It's a little bit charred there. Okay, so I'm taking out C23 as well, which has got some charring on it. Just give it a quick test perhaps. Ooh, that's clever, it dropped on the floor. And of course it's so tiny you can't see the thing. I'll be back now. Well, that literally took about 5 minutes to find that capacitor I dropped on the floor. Good grief. Absolutely bonkers. I had to get the light off and everything. It was absolutely unbelievable. Little fiddly components. Hopefully we can get that in there now. Not really testing as anything. Didn't expect it to. It looks pretty charred. Okay, so it says C23 is actually capacitor, 47.7 nanofarad. Okay, what's surprising? It's actually a 42 nanofarad capacitor, or 49, so it's 50 nanofarad, isn't it? So I'm going to desolder C22 next. Give that a little bit of a test. Soon, I think. Don't move it with a tip, it'll damage the tip. Use the soldering iron. Go. Hopefully, yep, straight out. Okay. So the round is the bullet on this. That says no. No part of unknown, which is logical really. I can't see that being a working capacitor. So C22 is testing as a 20 microfarad maybe. 8% ESR 0.07 ohms. Okay. It's possible it's still alright, but I think we'll just replace it. I might look at C24 as well, because that was around the area that was damaged. Okay, 50 nanofarad. So it looks like C24 is a... both of those, even though it looks a bit charred, is actually a working one. And they both have the same V-loss reading of 0.2. So I'm suspecting they're okay. So we put them back in, and we'll find a replacement capacitor, I think, for these two, and check the actual. So I'm going to suspect they're similar capacitors. We're going to check the circuit diagram and decide what we're going to do about replacing them with electrolytic. I'm fairly certain they're just 22 microfarad capacitors, which we should have something we can use in the capacitor box. That's a 20 something volts, so as long as we've got in well above the 12 volt headroom, we'll be fine. 15 volts. Okay, so we should be able to find something. And the 22. That's that 220. I think we must index these a bit better. I could actually go in the other box and get some axials out, which will look neater on the board maybe. Yeah, I'd probably put the ceramic in. It's only a transient suppressor in the power lines as far as I can see, but I have found a couple of axial 100 microfarad 25 volt capacitors, so I think they will fit in those just nice there and probably look a little bit more authentic. Of course we need to make sure we get the pos and neg the right way around, because it is negative that way. Okie dokie, so we're going to bend the pins on these and get those caps soldered in and make it a tidy job. So hopefully it's very close to that tip transistor, but hopefully we'll be alright with some. It looks better with the axials, I think. I don't know whether it looks so good with the negative showing. Maybe we'll change it so that the neg stripe is a little bit less visible. There we go. Just so when you look at it, it looks a little bit more like the original bullet caps. There we go. So it's probably a bit better hiding the neg stripe a little bit. Get some more of these. Obviously I got quite a few from recap spectrums and things. Okie dokie. So we do the same with this one. I think that we will make it so the neg stripe is a little bit less visible, but you can still see the value. No point in putting the old cap back. Well, they think they fit. All right, there. Look at that. That's just about right. And 25 volt will be fine. It's a little bit higher rating than the. Yep, that's fine. And like I said, we'll probably put the ceramic in instead of what was the charred one. We'll keep them all in a bag though. I'll keep all the original components for the job. That doesn't look too unauthentic. I think we'll probably get away with that as a repair. Okay. Not my best soldering job ever, I think. Oops, I bumped the camera with the light. Yep, they are soldered on, definitely. And assuming they are through hole. This doesn't flow through to the other side. There we go. We'll chop them off now. Trying to find the cutters. Ah, great. In the middle of moving my electronics lab upstairs, and I've left the cutters downstairs. Typical.